So then we get down to the normal cryptography stuff. We can come back to some of these other blockchain things later, or anybody that's interested can continue to do them even if I'm not demonstrating them. First, there's a little bit of math fundamentals. If you don't know your binary, you can learn 4 bits at a time with nibbles and 8 bits at a time with bytes to understand how to convert binary to decimal and hexadecimal back and forth. And so let me just demonstrate, say, the nibbles, and then I'll talk about the modular arithmetic, which probably, this is 1, 0, 0, 0, so this is the number of 1s, number of 2s, number of 4s, and number of 8s. So that's an 8, no 4, 2, and 1, so that's 8. And that's 0. And after you get, I think, 5 or 10 in a row correct, then you see a flag. So that's how these work, and you can turn in those flags in the usual system. But the modular arithmetic is the part that a lot of people are not familiar with. And this is where you need to understand when you're encrypting things, you're going to have a series of bytes. And after you encrypt it, you want each byte to turn into another byte. You don't want one byte turning into 2 or 3 bytes. So you don't want the normal kind of math where numbers can get bigger without limit. What you want is modular arithmetic, math on a ring. So here's a ring from 0 to 8, and that's it. So if you have 8 and you add 1, you have 0. If you have 8 and you add 2, you have 1. You just wrap around, you never leave the ring, so there's only a controlled space. So they call that modulus, and this is modulus 9, numbers 0 through 8, not including 9. And so 0 is 0, and 9 is 0. And 1 mod 9 is 1, and 10 mod 9 is 1. So you divide by 9 and take the remainder, is another way to look at it. And you can go all the way up. Here's 27 mod 9 is 0, and 18 mod 9 is 0. This is just 3 times around, and this is just 4 times around. And you can subtract, and you can have negative numbers. 0 minus 1 gets you 8. 0 minus 2 gets you to 7. So you can have addition and subtraction. And so you can add things. 1 plus 5 mod 9 is 6. 8 plus 3 mod 9 is 8. Plus another 3, it's 2. All right. And you have subtraction works fine, the same way it normally would. And you can have other moduluses like modulus 4. And here's modulus 6. So you have 0 through 1, 2, 3, 4, 5. And you keep adding rest around to 0. So that's modular arithmetic. And you've got a challenge here to solve a bunch of these, like 28 mod 9, that's 27 plus 1, so it's 1. 28 mod 8 is 24 plus 4, so that's 4, and on you go. And the next thing, let's go to modular arithmetic 2, because this is where it gets more interesting for people. So you see you have modular arithmetic, and you have addition, and you have subtraction. All right? You also have multiplication. So we did this already. I can just count the modulus 9. Now I can try multiplying. 2 times 9, modulus 9. I have 0. I go up to 9. I still have 0. I make another loop. I'm still at 0. So you can do it. You can also separate them. 2 mod 9 times 0 mod 9. Or this might, I probably should have made this a 9 mod 9. But that's 0. 2 times 10 mod 9 is 2 mod 9 times 10 mod 9. So this is 1. So that's 2. And, all right. So you can do multiplication on a modular scale. And so here's 2 times 9 mod 9. All right, now, if I do 2 times 5 mod 9, that's 2 mod 9 times 5 mod 9, that's 10, that's 1. So 5 is the multiplicative inverse of 2. 2 times 5 is 1. See, there is no division. There's addition and subtraction and multiplication, but there is no way to divide on this ring. So instead of having division, you multiply by the multiplicative inverse. So if you want to encrypt something, you would multiply it by 2, and then to decrypt it, you would multiply it further by 5. And the combination of multiplying by 2 and 5 would get you back where you started. That's why it's the multiplicative inverse. So here's 6. Now if you consider 6 mod 9, 6 times 1 is 6, 6 times 2 is 3, 6 times 3 is 18, that's 0. This doesn't pass through 1. It goes 630, 630, 630. There is nothing you can multiply 6 by that gives you 1. So there is no multiplicative inverse of 6. So if you were to try to encrypt something by multiplying by 6, there would be no way to decrypt it because that operation destroys information. All right, and here's 7. If I take 7 times 1, 2, 3, and 4, 7 times 1 is 7, 7 times 2 is 14, that's 5. 7 times 3 is 21, so that's 18 plus 3. 7 times 4 is 28, that's 27 plus 1. So I found the multiplicative inverse of 7 is 4. So I could multiply by 7 to encrypt something and multiply by 4 to decrypt it. And here's modulus 4. So just going around, same kind of thing. All right, so this is, that's multiplicative inverses, and they're not terribly simple to find or to use, and there's a challenge here where you get to figure that out. It's a multiplicative inverse of 9 mod 10. All right, so 9 mod 10, 18 is 10 plus 8. So I think 9 might be its own inverse. 9 times 9 is 81. I think, yep, 9 is its own inverse. You can multiply by 9 to encrypt, and you multiply by 9 again to decrypt. So that's the game. All right. And the last one of these is XOR. If you don't know XOR, it works like this. It works by bits. If you have 0 XOR 0, it's 0. If you have 1 XOR 1, it's 0. It's exclusive OR. It is 1 if these two are different, 1 and 0. Either way, if they're the same, the answer is 0. And this is really important in cryptography because remember how I said if you were to encrypt on a ring 9 with a number of 6, you could never decrypt because that encryption destroys information. If you have a pattern of 1s and 0s, let's say half 1s and half 0s, and then you XOR it with random keys, it will flip half the bits, so it will remain half 1s and half 0s. This is important. That's how Shannon measures information, probability of numbers. If you were to use a normal OR, then this would be a 1. And so 3 of the answers would be 1 and 1 would be 0. So feeding in a thing that is half 1 and half 0s would result in something that was 3/4 1s and 1/4 0s. And that means it contains less information. So you would have destroyed information with that transformation and there'd be no way to reverse it. So in encryption, you don't use information destructive operations like that. You carefully choose ones that preserve information, and XOR does preserve information. It can be undone. So you can do it in Python with the caret symbol 0, caret symbol is 0, 0 caret 1 is 1, so on. And so you can do longer numbers, bit by bit. 0, 0, XOR 0, 1. You just do the left bits separately. 0 XOR 0 is 0. And then the right bits separately. 0 XOR 1 is 1. So that's how you can do 2 bits. And you can do the same thing in Python. And you can do 4 bits. You just do them one at a time. So 1, 0, 0, 0, XOR 0, 0, 0, 0. The 3 right-hand numbers are all 0. The next one is 1. And you can therefore do 8 bits ASCII. All right. So that's the XOR, and there's a challenge where you practice doing some XORs. If you're not familiar with that, it's a good thing to do. So 8 XOR 0. XOR anything with 0 does not change it. So that's 8. 4 XOR 8 is, if I bring up a place to do some scratch pad. All right. So 4 is 0, 1, 0, 0. And 8 is 1, 0, 0, 0. So if I XOR them, I'm going to get 1, 1, 0, 0. And that is 12. So anyway, I mentioned that. If you are not familiar with the fundamental mathematical operations, this is a way to practice it. I'll stop this one.